Hello everybody, welcome to this week's video. So today I'm going to cover stress and strain, and before I get started, what I want to talk about is that for this entire class, which is about 7 weeks, every Monday morning you're going to receive a video that kind of covers a little bit of what we're going to do for the entire week. Instead of going through the theory, I'm basically going to go through some examples, one or two examples from each week's topics, and then if you have any questions you can just go through the theory that is posted in the PowerPoints and send me emails or send me a message on Blackboard if you have any questions. All right, let's get started. So the main point of strength materials, especially with stress and strain, is that we are trying to figure out what the internal loadings are. So what are our internal loadings? Which is usually shear, moment, and maybe torsion. Thermal stress is the other things that go into it as well. So let's worry about some stresses and strains as well. So for today, we're going to cover a little bit of stress and a little bit of strain, and also how to find internal loadings as needed. So for example, if you're given a question like this, you have a beam that is simply supported. So it has a pin on one side, and then it has a roller on the other side. And then I like to use different colored pens or pencils to kind of help us see what's going on. So we have a triangular load that diminishes over the distance. That is 4 kilonewtons per meter. And then we have our dimensions. This is 6 meters. And then we have our points. So this is point A and then point B. And then my question to you is, find, I forgot one more thing, apologize. So we also have, that's it. So the question is, find the internal shear and moment of beam. I make a lot of mistakes when I'm writing, so bear with me throughout every single video. I apologize. Beam AB. Alright, for something as simple as this, in order to find shear moment, and especially the internal shear moment, all you have to do is basically make a cut, and I'm going to use yellowish pen to make the cut. We're going to have to make a cut somewhere in the middle. This is because for you to figure out what the stresses are, what's going on the inside, why your beam is actually behaving the way it is, you have to look on the inside. Now, before we look on the inside, what we have to do is look on the outside, figure out what the support reactions are, and also the effect of the external load on the beam, because all of those things play a part in finding the internal shear moment. Okay, so we're going to go with step 1. I don't always write step 1, but for today's video, we're going to go ahead and do that. Step 1, we have find the support reactions. So, if we draw the free body diagram. And henceforth it's going to be called FBD. So I'm just writing that out so we all know. I'm just going to redraw this. This is point A, point B. I'm going to try to keep the same color so we're all aware that if I use green, it just means the load, the external loading as well as reactions. So this is 4 kilonewtons per meter. This is AY, AX, and then BY. And we're gonna Sorry about that. We're going to use our blue pen to find our dimension, which is 6 meters. Alright, so since this is a simple problem, I'm not going to talk too much because this is just a statics review, right? We're trying to find our support. So summing forces in X, and I always use from left to right as a positive direction. We have our AX is equal to 0. And then what I'm going to do is skip ahead and go to moment. We're going to sum our moments about point A. I always do that. There's really no reason. You can do point B as well if you want. So point B, since B is going counterclockwise around point A, we have BY times 6 meters minus, because this triangular distributed load is going clockwise around point A. So I'm going to get my red pen. We're going to say that since it's a triangular load, it's going to act 1/3 of 6 meters away from point A. So this triangular load, if you're trying to find a point load from it, it's going to be 1/2, because it's triangular, times 4 kilonewton per meter times the distance, which is 6 meters. All right. So if you're trying to do this math, it's going to give us so we have apologize 1 second, so 2. So we're going to have 12 kilonewtons. So going back to where we were before in the equation, this distance right here is 2 meters. So we have 12 kilonewtons times 2 meters is equal to 0, which means that our BY is 4 meters. Okay, which is great. So now that we found this, we're going to make a cut. Where's my trusted blue pen? We're going to make a cut. So step 2, make a cut in the middle, or we're going to say somewhere on beam. Okay, so before we do that, I forgot one more thing. We're going to find A. So we're going to sum forces in the Y direction, and up is always positive in my books. So AY plus BY minus 12 kilonewtons equals 0, which means that AY is equal to 8 kilonewtons. This should be kilonewtons as well. Okay, now we're going to make a cut somewhere in the medium, so we're going to draw free body diagram. So right here we have so let's say that this is actually, let's change it to 3 meters. I'm going to make this a little bit shorter. So 3 meters. And we're going to have our distributed load. And we'll talk about that in just a second. And we're going to have BY, which is equal to 4 kilonewtons. And then we have our internal shear moment. So we have shear, we have our normal force, and then we also have our moment. So this is M. All right, now that we have these guys, question for all of us, and that's something that we should think about for a second. What is the value of the largest part of the triangular load? It is not going to start at 4, but it's going to start at a version of 4. So using similar triangles, we're going to say that we have, since this is 3 meters, we're going to say this is 3 meters over 6 times 4 kilonewton per meter. All right. So, and like I said, it can really be cut anywhere on this, and it should still give me the same answer. Okay. So, really quickly, we're gonna draw the dimension here, which is 3 meters. Okay, back to our black pen. Almost done, guys. Almost done. So first step is that we have summing. Let's start with summing moments. Okay. So summing moments about point. Let's call this point D, which is equal to 0. We have by times 3 meters. And remember that this is right here in the middle. So we have 1/2 times 3 over 6 times 4 kilonewton per meter times 3 meters. So that's going to give us our concentrated load. So times 1 over 2 times 4 times 3. And it gives us 3 kilonewtons. And that's acting only about 1 meter away. All right. So by is going the positive direction, so it's by times 3 meters. And then we have 3 kilonewtons from here, from the concentrated load version of the distributed load. That's going about 1 meter away. And then we also have our moment, which is going counterclockwise, so plus m. I don't know if there's something else I'm missing. 1 second. Right. Is equal to 0. So remember that by is 4 kilonewtons. So we have 4 times 3 minus 3.